Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a mini-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Episode 4, Tools of the Trade. In the last episode, I talked about the progression of scientific ideas from the hypothesis stage all the way to something being a scientific theory. As a reminder, the key ideas here are that scientific hypotheses must be able to make testable predictions about the behavior of physical systems. All hypotheses are subject to modification or rejection based off new evidence. And what differentiates the terminology used to label an idea, what makes a scientific theory different than a scientific law, is how explanatory the description of the system is. In considering this progression, it should be noted that the process is founded on two things. First, it is an empirical process, which is to say that the validity of an idea is based on observation of the physical world. Second, the process is a cyclical one rather than a linear one. No matter what the idea or description is called, whether it be a hypothesis, law, or theory, the process of testing the idea is ongoing. In fact, it can be said that the more radical a prediction the hypothesis can make, the better. To use a well-known example, let's think about looking at white swans. Let's say that you live in a place where only white swans have ever been observed. If you have a hypothesis that says there are only white swans, that's okay, but it's not as useful as a hypothesis that says that most swans are white, but if you look in, say, this particular region, you'll actually find black swans. So, what makes the second hypothesis better? Well, in the first place, it's easier to test and easier to show either correct or incorrect. In the first hypothesis, the observer sort of has to look all around at a whole lot of different places and hope to see a non-white swan somewhere in order to prove the hypothesis wrong. The second hypothesis is much more precise in its prediction and thus much easier to confirm or refute. You have to look at the one place the hypothesis says there should be black swans and see if they're there. If there are black swans, great, the hypothesis is immediately shown to be correct, and if there aren't, then it's definitively falsified. Additionally, finding more white swans doesn't actually tell us much in the case of the first hypothesis. While each white swan confirms the hypothesis, it doesn't eliminate the possibility of finding a black swan that'll refute the whole thing somewhere down the line. On the other hand, the second hypothesis does a much better job of telling us what to look for and where to look for it, giving us a much better chance of coming up with a definitive result. In science, this drive towards precision is very important. The more precise we can make both our ideas and the predictions they make, the more we will learn about the physical world, and thus we'll be able to arrive at relationships that are more useful in understanding how the physical world works and why it might work that way. In doing science, researchers will use a couple of tools to help them refine and better express their ideas. One of the more useful things that a hypothesis can use in explaining something is called a model. A model is a representation of reality that usually simplifies the system while changing its scale in such a way that a specific set of aspects of the system become more easily understood. Now, there are many examples of models we can discuss. One example is a plastic model one might buy at a local department store of a plane or a ship or an automobile. Such models, of course, aren't the real thing, but are instead representations of what that thing might look like in some detail. They usually scale the object by making it smaller, and they never include all the little bits and pieces that make up the entire system, i.e., in an automobile model, the engine and transmission are never fashioned so that they're tiny replicas of all the moving parts in a real automobile's drivetrain. However, they do allow someone to see the entire vehicle or plane or ship in enough detail to understand how the parts of the system relate to the whole. Another example of a model might be a road map. The map, again in this case, is a smaller representation of the real land, and its purpose is to give a good sense of the two-dimensional relationships between various locations and geographical features. The thing that many maps don't do as well is show the elevation changes or the type of vegetation present in the landscape. Finally, depending on the scale of the map, smaller towns and historical markers might be omitted entirely. In science, we will often use models to help understand various parts of a hypothesis while leaving other aspects out so as not to make things too confusing. Including every single asteroid and comet in a model of the solar system would likely make it far too cluttered if what one wants to understand is the spacing between the planets and how they move around the sun. This simplification is a key aspect of all models and is vital to their usefulness. Oftentimes, it is possible to have more than one kind of model for the same physical system. Each model will emphasize a particular aspect of the system while leaving others out in order to help the user understand that thing. In our maps example, it's possible to have road maps, elevation maps, vegetation maps, and many other kinds of maps for the same part of the land. The difficulty with this is that if only one type of model is used, it is possible that key relationships will be missed between important variables. In these cases, it can be helpful to combine two types of models together in order to see if those relationships exist. As an example, it's probably useful to combine maps of rainfall, elevation, and vegetation together in order to see how those things might relate to each other. Doing so might allow us to answer the type of question that goes, does a certain species of fern only grow below a certain altitude when the average annual rainfall exceeds a certain amount? A map like that would probably go a long ways towards answering that question. The difficulty, of course, with these more complicated models is that they can be hard to construct, and they may become confusing due to having too much information represented on them, thus defeating the purpose of the model in the first place. This is where things like computer visualization tools can be very, very helpful as they've been developed over the last few decades. One thing scientists and science educators must be very careful about is to not introduce incorrect ideas into their model when they simplify the real physical systems to make them. As an example, frequently one can find illustrations of the planets in the solar system where the planets are all lined up in a straight line away from the sun. Now, this never actually occurs in the solar system, and having a picture where the planets are shown in that configuration has a pretty good chance of introducing an incorrect idea into a student's mental picture of how the planets are organized in their orbits around the sun and how they move. One final note about models is in order here. Models don't actually have to be physical. Many scientists use mathematics to describe aspects of how a system works. These mathematical models can be very efficient in describing the system and will allow for predictions of the system's behavior to be made in very powerful ways. Frequently, these mathematical models can be programmed into computers that can solve the equations in such a way that the state of the system can be simulated well into the future, even when the system is very complex. An example of this can be found in modern weather forecasting. In this case, the state of the Earth's atmosphere is measured in several ways, such as its temperature, water vapor content, barometric pressure, wind speed and direction, and so on. And these measurements are taken at several places around the globe. That data is then given to a computer model whose job is to calculate what the atmosphere will do in the future given its present state using the physical relationships that have been determined by physics and chemistry and have been programmed into the model. This can be very useful in determining the path of a hurricane or the intensity of a severe weather system that might bring tornadoes or heavy rains and flooding to an area. Every weather forecast you and I receive has some foundation in a computer model based on a description of how the atmosphere works. Another tool scientists will often use in attempting to understand how certain systems work is what might be called an organizing principle. This approach was first formally pioneered by Francis Bacon, and the idea is to gather all the data available about a variety of things that might be related and organize those things around some idea. Bacon's example of using this was to organize physical phenomena around the concept of heat. Things that are hot and then also give off light sort of go in one intellectual pile, while things that give off light but are cool go in another, and things that are hot but don't give off light might go in a third group. By organizing data in this way, the hope is that a scientist will be able to see a pattern emerge that will give clues as to some underlying structure or cause for the behavior. A really wonderful example of an organizing principle that probably most of you are familiar with can be found in the periodic table of elements. Almost everybody has seen one of these things hanging in a science lab somewhere. It's almost the iconic thing that sort of identifies a room as a place where science is done. Now, while we'll discuss this in greater detail down the road a bit, let's just say for now that the modern table was originally the work of Dmitri Mendeleev. As a chemist, he noticed that certain types of elements had specific ways of reacting or interacting with other types of elements. By grouping these together, Mendeleev began to see regularities in the way the chemical and physical properties of the elements were distributed. He organized this chemical data and saw that a specific pattern emerged and was thus able to predict elements that were as of yet undiscovered. While Mendeleev didn't have a good understanding of what led to these regularities, his table not only led to the discovery of a number of elements, but it also guided much of the thinking about electronic structure once the atom was better understood after the discovery of the electron. Similar organizing principles were used to help guide the discovery of a number of subatomic particles once it was understood that the atom wasn't the smallest thing in the universe, and they were of great help in the discipline of particle physics. When an organizing principle is discovered, it provides a strong clue that there is a deeper, underlying cause at work in ordering the behavior of related systems. They can guide the investigator to looking more deeply into the systems being studied in order to uncover those physical relationships or causes giving rise to the structured behavior shown. This is one of the ways and one of the tools that scientists will use when moving an idea from being a scientific law to a scientific theory. A question a lot of my students will ask is they wonder if science is always as cut and dried in its approach as I've sort of presented here. While a good deal of scientific investigation is highly structured and planned, not every discovery is made of as part of an organized investigation. Some discoveries are stumbled upon unintentionally. While there are those who would say that these discoveries are made by quote-unquote accident, I'm not a big fan of that term. It is said that Louis Pasteur once commented, "Chance favors the mind that is prepared." The term that is more often used is called serendipity, and it means an unintended discovery that has been made in a prepared environment. The story of the discovery of Teflon is quite instructive in thinking about this. The scientist who made the discovery, a man called Roy Plunkett, was working for DuPont trying to create a chemical compound that would act as a refrigerant much like Dow's Freon. In the course of his research, Plunkett mixed together a variety of chemical gases in large stainless steel containers with expectations that they would react to form some sort of a liquid. When he later looked in the containers, he found that there wasn't a liquid in them and that there was a substance coating their insides. Now, since Plunkett was an excellent organic chemist, he had been very careful about conducting his experiment, being sure to record all of his steps and measurements. This allowed him to quickly understand that the gas had undergone a process known as polymerization, which meant that long chains of molecules had formed, which had then stuck to the walls of the container. He was then able to run a series of tests to determine the exact makeup of these polymer chains and how they were constructed. Additionally, he could reproduce the chemical reaction chain for the substance, otherwise known as TFLE or Teflon, and thus industrialize the production process. By knowing the process and the final product, DuPont was able to apply for and receive a patent for the compound, which is now used in many different types of applications. Was the discovery unintentional? Sure. Was it an accident? I'm not sure that accident is the best word to describe the process that took place. Plunkett's deep understanding and knowledge of chemical processes not only allowed him to set up the right condition for what had happened, but they allowed him to understand what had taken place and then begin testing the results, even though those results weren't quite what he had expected. Had Plunkett been sloppy in his work or lacking in chemical knowledge, the discovery would never have taken place. There are lots of famous discoveries that were initially made unintentionally. That's going to happen when people investigate systems they either haven't worked with before or in ways that are new and unique. What's important to understand is that these discoveries are still made within the structure of scientific inquiry and that the process still works in the same way once the discovery has been made. In a way, it's like asking a question and then getting an answer you didn't expect. If you investigate the answer, you realize that not only does it answer the question you asked, but that the question might be bigger or different than you thought it was, and that will lead your research off in a whole new direction. To be honest, this is part of the great adventure that is science, and for many of us who participate in the scientific endeavor at the professional level, the possibility that we might stumble across something unexpected is part of what drives our work forward. The final tool I'd like to mention is different types of reasoning that can be helpful when attempting to express and analyze scientific ideas and thoughts. While I'll have a lot more to say about systems of reasoning and logic in a later series of podcasts, let me get a few of the basics out of the way right here. Reasoning usually happens in the form of making of what is called an argument. Now, when I say argument, I don't mean one person verbally disagreeing with another. Instead, what is meant in this context is that a person will draw a conclusion for one or more premises. A premise is a statement of fact or belief. It's an assertion of the truth. The sky is blue would be an example of a premise that could be used in an argument. So is something like all human beings are mortal, and an object, when released from rest near the Earth's surface, falls towards the ground. When making an argument, a person will draw conclusions about something, in the case of science, the physical world, from the premises that have been stated. The most basic form of reasoning, and the one that is most familiar to most folks, is what is known as deductive reasoning. In this form of reasoning, the conclusions of an argument are said to be contained within its premises. The classic example of a deductive argument is: Premise 1. All human beings are mortal. Premise 2. Socrates is a human being. Conclusion: Socrates is, therefore, mortal. In this form of reasoning, if the premises are true, then the conclusion must be true as well. This is the type of reasoning used in mathematics. In mathematical research, the mathematician begins with a set of things that are assumed to be true, called axioms. From the axioms, proofs of other things that therefore must also be true are developed using deductive reasoning. If you remember your high school geometry course, you may recall doing a lot of these sorts of proofs for things in the two-dimensional plane, i.e., the shortest distance between 2 points is a straight line, and so on. Now, if the initial assumptions are shown to be false in a particular case, then everything that has followed from them is also held to be false. For example, the shortest distance between 2 points on a curved globe is not a straight line, but a curved arc. The old rule no longer holds true because on a spherical globe, there are no flat, two-dimensional surfaces. In mathematics and deductive reasoning, when we say that we have proved something, what we mean is that we have created an argument where the conclusions must be true if the premises are true. Aristotle made one of his many contributions to philosophy by gathering and clearly stating the fundamental rules of deductive reasoning for later philosophers and mathematicians to use. Science uses deductive reasoning insofar as it uses mathematical models to describe physical reality. Once a mathematical relationship is found that accurately describes the behavior of a system, that relationship is then treated like a mathematical axiom, and the scientist will try to work out what must be true for that if that axiom is true. These conclusions are then shared so they may be tested. The reason for the testing is that since the truth of the conclusions is contained within the truth of the premises, if the premises are wrong, the conclusion would be as well. Thus, by testing whether the conclusions are true, we are indirectly testing the validity of the premises as well. This form of reasoning, however, is not the only type of reasoning used in science. In fact, it's not even the dominant form of reasoning. This is because we can never know if any stated premise is always true for every circumstance. Thus, science also uses the forms of reasoning known as inductive and abductive reasoning. Inductive reasoning is a type of reasoning where even if the premises are correct, the conclusion might be incorrect. Induction, as a process, is the process of arguing from a specific known case to a general assumption about how everything works. Now, an inductive reasoning argument would look something like this. Premise number 1. It has been observed that the first 11 eggs in a carton have all been rotten. Premise number 2. All of the eggs in the carton have the same sell-by date. Conclusion. The 12th egg in the carton will also be rotten. Another type of inductive argument might be, premise, every morning when I've turned on my computer, it has not exploded. Conclusion, when I turn on my computer this morning, it will not explode. Now, what can be seen here is that even if the premises of these two arguments are true, the conclusion might actually be false. In an inductive argument, it is possible for the premise or premises to be true and for the conclusion not to be. It may turn out that for some reason, the 12th egg has not spoiled and could be used safely for cooking. Of course, the only way to know that is to perform an experiment by breaking the egg open and taking a look at it. As seen in the example of turning on your computer, we use inductive reasoning all of the time to get through our days. When we drive a car, we have a great deal of confidence that when we turn the steering wheel clockwise, the car will turn to the right. For most of us, this is completely based only on our experience. It's only for a few with training in engineering that it's also based on an understanding of the mechanical systems that comprise the steering mechanisms for the car. In either case, what we are really doing is basing our future expectations in a general way on the past specific experiences that we've had. If the mechanical system in the steering of the vehicle malfunctions, the car won't turn to the right when we move the steering wheel clockwise, and our expectations will have been wrong. As you can see from this second example, science uses inductive reasonings as one of the tools to understand the world. In medical science, it was discovered that some individuals who had a condition known as Down syndrome also had 47 chromosomes instead of the normal 46 found in most people. Researchers formed the hypothesis that it was the 47th chromosome that caused Down syndrome. They went back and tested the hypothesis by checking many more people with the condition and found that each of them also had an extra chromosome. From this, they made the following argument. Premise: all people who have Down syndrome and who have had their genetic code examined have been found to have an extra 47th chromosome. Conclusion: all people who have had or will ever have Down syndrome also have an extra 47th chromosome. As you can see, this is an inductive argument. While it certainly seems reasonable to draw this conclusion from the premise, there is a possibility, no matter how remote, that one day someone with Down syndrome might only have 46 chromosomes and the condition could be caused by something else. Science does this kind of reasoning all of the time. When Isaac Newton put forward his universal law of gravitation, he didn't actually go to every place in the universe. Instead, he looked at a fairly limited number of systems, i.e. the moon's orbit around the Earth and the planet's orbits around the sun, and inductively concluded that the physical cause of their motions existed at all places in the universe. His law was then applied in each new case or situation to see if it could accurately explain the motion of an object that was being observed. It wasn't until the early 1900s that Newton's model of gravitation was shown to be inadequate to explain certain observations, most notably of the orbit of the planet of Mercury, and Einstein's model of gravity, as expressed in the theory of general relativity, could replace Newton's model. The problem with inductive reasoning, of course, is that it can't actually quote-unquote prove anything the way that deductive reasoning does. This is known as the problem of induction and was first clearly stated by a philosopher called David Hume. We'll return to this problem and some of the proposed solutions to it in a later series of podcasts. Finally, the third type of reasoning scientists use is called abductive reasoning, or inference from best explanation. Now, to be clear, and so I don't get yelled at by real philosophers who might listen to this podcast, there are some in the field of philosophy who claim that these are two different things, and other philosophers who say that not only are they the same thing, but they're just another form of inductive reasoning. We'll leave those arguments and discussions to the experts, and I'm just going to try to cover this in a general sense. Abductive reasoning is really reasoning from the conclusions back to the premise or premises. Another way to look at this is to say that by looking at the effects, we then reason back to causes. The typical argument of this sort goes like this. Observation, or perhaps premise 1. When I woke up this morning and went outside, it was sunny, but the lawn was wet. Observation, or premise number 2. It's not humid enough for dew to have formed. Inference, or conclusion. Since I don't own a sprinkler system, it must have rained last night. Now, this sort of reasoning is the staple of any kind of murder mystery. You know the narrative. A person is found dead, and the detective or detectives have to reconstruct the circumstances that led to the death in order to catch the killer and bring them to justice. Of course, if the mystery is any good, there are going to be twists and turns to the plot that will show the limitations of abductive reasoning by not arriving at the conclusion that the abductive reasoning would have suggested is the most likely. Just like with inductive reasoning, the inference can't actually be proven true unless specific observations can be made. And since this form of reasoning is often used to determine past events, it can be really hard to go back and make an observation of something that has already happened. In our example, while the best explanation might be that it rained last night, it is possible that you have a particularly generous neighbor who, while walking his dog in the evening, noticed your grass looked a little brown, and so set up his sprinkler in your yard early that morning to water it. By the time you woke up, he had finished his watering and had removed his sprinkler. Unless you interview all of your neighbors, you can't actually eliminate that possibility. A scientific example of this is found in what is known as the Tunguska Event. Carl Sagan has a wonderful discussion of this in his book Cosmos, which I will summarize here. In 1906, there was a physical occurrence of an explosion in a region of Siberia in Russia known as Tunguska. The explosion was said to be very powerful, and when investigators went to examine the region, they found trees flattened to the ground for miles in every direction. When mapping the direction the trees fell, they determined the point at which the explosion must have occurred and that the blast wave must have radiated outward. So the question became, what caused the explosion? Now, there are lots of possibilities. People have suggested that it was an alien spacecraft that crashed to the Earth, a mini black hole, a comet that vaporized just before contact with the ground, an asteroid impact, and any number of other things. As scientists have worked to reconstruct the cause of the explosion, they've tried to go back and gather additional observations that will rule out some explanations while making others more likely. As an example, if an alien spacecraft crash had caused the explosion, one would expect to find some kind of wreckage at the impact site. Even though very thorough searches have been made, not even the smallest piece of alien technology has been found. This observation makes such an inference very unlikely. The same can be said to be true for a mini black hole. If a black hole had slammed into the surface of the Earth in Tunguska, one would expect that there would have to have been a second such explosion as the black hole exited out of the South China Sea a few minutes later. While barometric stations all around the world recorded the atmospheric pressure wave of the first explosion, none recorded a second. This observation significantly reduces the likelihood that the black hole explanation is correct. This leaves the comet and asteroid impact hypotheses as the most likely explanations. These two both explain the observations made and are not ruled out by them. Finally, in the case of an asteroid impact, one would expect to find both an impact crater and large fragments of the asteroid, both of which are absent in this case. Thus, the best explanation, given the available evidence, is that a small cometary fragment entered the atmosphere and exploded a short distance above the ground. The explosion vaporized most of the fragment's ice as well as dispersing its solid material and wouldn't have left or formed an impact crater for investigators to find. While other explanations can't be deductively ruled out, this is the best explanation given the data, and thus we infer that it is true. Such arguments are often found in scientific fields that are what we call historical, in that they attempt to reconstruct past events from evidence that was left behind. Geology is an excellent example of a science that uses this sort of reasoning frequently. For both inductive and abductive reasoning, a way of estimating the likelihood of a conclusion being correct has been developed using some mathematical reasoning in the fields of statistics and probability. Known as Bayesian probability, this statistical approach to determining how likely it is that a conclusion is true will be discussed in that later series of podcasts on the problem of induction. Understanding this idea that both induction and inference are not foolproof leads investigators to try to work harder to design experiments and make observations that create evidence and data that allow for the strongest inference possible. Another way to say this is that the best experiments are those where the results rule out as many hypotheses as possible while confirming only one. To do this, there are three conditions that are necessary. The first condition is that there need to be alternative competing hypotheses that attempt to explain the behavior of the same system. The second is that an experiment or observation must be designed for which the competing hypotheses will make very different predictions for the behavior of the system. The third condition is the experiment, when conducted, should get clear and unambiguous results that rule out all but one of the hypotheses. One of the most famous historical examples of this sort of experiment is known as Young's Double-Slit experiment. The American Institute of Physics actually called this one of the 10 most beautiful experiments ever conducted. Now, at the end of the 18th century, there were two competing hypotheses about the nature of light. One hypothesis, put forward by Isaac Newton, claimed that light was made of small corpuscles or particles that traveled in straight lines from a light source. Another hypothesis, developed by Christian Huygens, said that light was a wave that traveled outward from the source, like ripples in a pond travel outward from the point where a stone has been dropped into the water. Now, it should be noted that there was observational evidence to support each of the two hypotheses, though, due to his tremendous stature in the scientific community, the hypothesis of Newton was more broadly accepted during the late 1700s. In 1801, Young devised a brilliant way to test which idea was correct. What he did is he passed light through two slits made side by side in a screen. Once the light passed through the slits, it was allowed to hit a wall. Now, if Newton's hypothesis was correct, it would predict that the pattern on the wall would be that there would be two bright lines separated roughly by the same distance as the slits in the screen. If Huygens was right and light was a wave, then the light would spread out from each slit and would do what we call interfere with the light wave coming from the other slit. This interaction would produce a pattern of alternating bright and dark lines whose spacing could be calculated. Now, if this all sounds a little bit confusing, what I've done is I've put up some Java interactive simulations that will allow you to see this phenomenon at the podcast website, www.thescientificodyssey.typepad.com. And I've included those diagrams to help you see how the experiment was performed and what the predictions of the competing hypotheses were. So, what we have here is the first two conditions for a great experiment. We have competing hypotheses that made vastly different predictions about the outcome of the experiment, and we have an experiment that can test each of those predictions. When Young performed the experiments, the results clearly and unambiguously showed that Huygens' prediction was correct, thus resolving the controversy. Well, at least until the work of a German physicist in around 1905, but that's a story for another podcast. By having these conditions, we can draw very strong inferences with a high probability that the conclusions arrived at from the evidence will be accurate. Such experiments are much easier to construct when the systems being studied are simple, and thus the hypotheses can produce clearly different predictions. In areas of study such as the social sciences, these sorts of experiments can be much more difficult to construct due to the high level of complexity of the systems being studied, i.e. the stock market and economics, and in the difficulty of controlling all the variables. The next podcast will be the last in this introductory series on the nature of scientific inquiry. While we spent a lot of time talking about what science is and how it's done, there are a number of misconceptions about science that I think it will be useful to explicitly address. Between now and then, you may find it interesting to do the following mental exercise. In your mind, imagine what you think a typical scientist looks like, how he or she might act, and what he or she does. See if you can think of a fictional character from a book, movie, or TV show that you believe really encapsulates what you see a scientist being and doing. This will help you prepare for what comes in the next podcasts, Misconceptions about Science. Until then, full sails on your journey.